Okay. All right. So thanks everyone for coming. So the tutorial with Jacob is going to be generally about blockchain technology and cryptocurrencies. And I think what we decided, kind of the overarching goal of what we were going to do, was just going to try and make kind of like what's out there, hopefully a little bit more accessible to people from the EC community. And so the first part of the tutorial, I'm going to give a simplified view of cryptography. And I'm also going to try and give a short pitch for kind of like what's already out there that is, I think, exciting for the EC community. Okay, so the first part of the tutorial is going to be on cryptography. And what I'm going to do is I'm just going to try and overview some common cryptographic primitives that are used in the cryptocurrency literature. And like I said, my goal here is I would like to make this aspect of blockchain research more accessible to someone with an EC background. For those of you who do know some cryptography, I just put up here a list of what I'm going to present. So you can kind of get a ballpark of like how much you already know, or or if you want to like zone out and come back in later. And throughout, though, I am going to highlight some canonical applications, including some applications in pure auction theory. And basically, the point of this is just to give you a sense of demystify some of these terms that are being used, and try and present them in an EC accessible way, and then convince you that this stuff is useful to know. And then in the last short bit, I'm just going to give you a very, very quick peek at some stuff that's already out there in blockchain plus mechanism design. And basically, I hope you just take away from that like, okay, there is pretty cool research going on, and it would be great to have more of that at EC. Okay, so now I am just going to dive into a very brief tutorial on cryptography. Okay, so first, I want to give a quick disclaimer, which is that formal cryptographic definitions are generally massive. They're very formal, and they reference computation. They're based on assumptions, and in general, what provably secure means to a cryptographer is provably secure under some assumption that we generally believe to be true, and sometimes those can be pretty unwieldy assumptions. So this is necessary, and that's necessary because cryptography is hard, and you want to understand precisely what kinds of adversaries your protocol is secure against. So what I can't promise to do is give you a simplified view of cryptography that's also mathematically rigorous and good enough for state-of-the-art research. The downside of this is that I think formal cryptography can be pretty inaccessible, and even I've taken graduate courses in cryptography, and I did research in cryptography when I was an undergrad, and I still find some of the formal definitions to be inaccessible and to take me a lot of time to process. So what I'm going to try and do in this talk instead is I am going to give precise and formal definitions, but I'm going to give precise definitions of things that technically don't exist. So they're going to be very strong constructions. And because they're so strong, they don't exist. But it really does get the main idea across of like what a cryptographically secure digital signature scheme does, or a cryptographically secure hash function. So just to repeat, I am going to give you like a formal definition, and this is a formal definition that I hope will be like accessible, and like you can interact with it, and it does capture something about what these primitives actually do. But I just want to be really clear that like if you want to do state-of-the-art, generally secure cryptography, there's no way to get around interacting with the very formal definitions that I'm not going to get into. Okay, but I hope that you'll still get all the main ideas of what this stuff does. So now I'm going to get started, and just kind of from here, I'm just going to dive right in, and I'm going to go over some basic primitives. And these are hash functions, commitment schemes, and digital signatures. So let me dive right in to what is a hash function. So a hash function, it's just a function. It has some domain. I don't know if you guys can see my mouse, but I'll use my mouse as a clicker, which hopefully works. So it's just a function with a domain and range. And typically you should think of the range as being significantly smaller than the domain. So for example, how this is used in Bitcoin is the domain is like all possible blocks that are at most 3 megabytes large, and the range would be a 256-bit string. Okay, so what's a hash function? Well, first it's a function, right? So if you query h on the same input multiple times, it should give you the same output, right? So that's necessary. And the thing that makes it a hash function versus, just any old function is it should be the case that if you haven't queried h of x yet, then you believe that h of x is uniformly random over d. Okay, so it's basically a uniformly random function everywhere you haven't yet queried it, and anywhere you have queried it, it's still a function. Okay, so it's not just a random number generator, right? Because if you query it on the same input, it has to give you the same output. But aside from that, it's basically outputting a random number. And the key thing that makes these hard to design in practice is that this guarantee is supposed to hold even if you condition on other queries to h. So even if I queried h on x minus 1 or 2x or every integer from 1 to x, and even if I have any other information, like I inspected the code used to write h and all of that, it's still supposed to appear uniformly random to me. Okay, so that probably seems like it'll be a little bit hard to get in practice. So here's an alternate view that may help through the lens of like, well, what if what if you just like trusted someone to implement a hash function for you? What would that look like? Well, it would look like this. The trusted entity would just draw a uniformly random function, and then they would not tell anyone else, including you, what they did. The only thing they would do is they would let you ask queries of the form, what is h of x? But they would never let you see the code they're using to run h. They would never reveal any information that they didn't have to, aside from answering queries. So imagine if you had something like this, this is, I think, how you should think of a hash function. Okay, now, oops. Okay, now, of course, in practice, we don't have this trusted entity who's doing everything for us. And in fact, what we have is the same hash function is used over a long period of time. So in Bitcoin, for example, they use SHA-256, and there's public code that everyone knows to compute h, right? And so what makes the cryptography very hard is you have to make it the case that you really believe that even if I show you all of the code used to compute h, and even if I show you h of 1, h of 2, h of 3, h of 4, h of 5, and even if you see all of that, still you don't have any useful information to predict what h of 6 is going to look like. Okay, so that's how you should think of a hash function. So what I want to do now is just very quickly give you kind of like some canonical uses to have in mind to help internalize this. And then maybe at the end of this, I'll do a quick pause just to see if there are any questions. So one use of hash functions that occurs in blockchains is called a hash pointer. So one thing that you want to do in a blockchain, you want to point to another block. And you want to do this in a way that doesn't require you to like take the entire block and put that in your next block, because then the blocks are just going to become enormous. You want some pointer. And a good thing to do is to just use the hash of B instead of B. And a representative concern you might have is you might say like, well, wait a second, what happens if the attacker originally produced a block B and the hash was h of B, and then I included a pointer to their block B, and I used Y to be that pointer. And then the attacker later says, no, that, B was not my block, it's B prime. And you'll see that I'm telling the truth because h of B prime is equal to Y. So this is a concern. So this is called a hash collision when this happens. And you can kind of see if you have this ideal construction that I proposed, where it's really uniformly random every time you query a new input, that the probability that you actually find a collision to the specific block is extremely small. And so what that means is that, even if you've heard of this, the birthday paradox, that if you just want to find any collision at all, you need to query at least the square root of the size of the domain things just to find any two inputs that hash to the same output. And, if the range is 2 to the 256, then that's 2 to the 128, and no one's going to query that many inputs before the universe ends. Okay, so this is a property, and then of course how it works in practice is you claim that your hash function is collision resistant, or you assume it's collision resistant or something. You just assume that or make a claim about that directly without going through the ideal construction. Second canonical use, well, now canonical due to Bitcoin, use of this is proof of work. So for example, maybe a thing that you want to do is you want to select a miner proportional to their rate of computing H. And you have this plan, which is what Bitcoin does, is you pick the first miner who produces a block B in randomness R such that the hash of BR is less than some number. So you say this means you have to try a lot of hashes in order to get something that's small. And a second representative concern is that, well, maybe I'm really good at algorithm design and I can do something much more clever than just try a bunch of different random numbers and hash over and over. And I'm going to come up with an algorithm that's going to cleverly pick some block B and some randomness R, and it's going to be a fancy algorithm. And this ideal construction has this property that's now called puzzle friendly. Right? So puzzle friendly just means that actually the best thing that you can do, there's no faster algorithm. The best way to find an R for any B, the best thing you can do is just to do random queries. And so again, what I want to point out is that this ideal construction clearly has this puzzle friendliness property. In practice, what you do instead is you have some construction and you want to claim that it's puzzle friendly. Okay, so so that's all I wanted to say about hash functions. I'm going to minimize my screen for a second just to see if there are any questions on this or to try and gauge how the pace is going. But so this is an ideal hash function. Again, you can either think of it in terms of the first bullet, the first set of bullets, or the second set of bullets. But in general, it's a uniformly random function, except it's consistent every time you query it. And importantly, somehow its code is going to be publicly posted, and it's still going to appear uniformly random to you. Okay, and so a quick reminder, I think this is a perfectly fine and formal way to understand what a hash function is doing and to remember what a hash function is. And I hope that this makes, when you read about hash functions used in cryptocurrency literature, that it makes it more accessible. Still, there is no efficient ideal hash function. So just be careful if you ever want to use this in your own research. Make sure that you consult some formal text, or you're a little bit more informed about what you need to assume than just this slide. But I think this slide is sufficient to start reading other people's works and to start understanding how hash functions are used, or to start understanding whether you want to use hash functions in your own research. So I'm going to take a quick pause just to check in on Gather. And so the question I saw in the chat is, what was the 2 to the 185 for? Why 185? So the 185, I think, is close to what Bitcoin uses in practice. It's just, so you want this to be, you want this 185 to be some number that's much lower than 256, so that it is hard, that you have to try lots of times, in this case, like 2 to the 71 before you succeed. And this is kind of like tuned automatically by Bitcoin to make it the case that someone succeeds roughly every 10 minutes. So as there's more hash power in the network, this 185 would go down. As there's less hash power in the network, it would go up. Okay. All right. So I'm going to move on to primitive number 2. And the second one is a commitment scheme. And here's how I'll describe it as in this ideal language. So say that you have access to an ideal hash function, using the language I used on the previous slide. Then commit is just some function that takes as input a message X and randomness R, and just outputs the hash of X and R. And what does it mean to reveal a commitment? Is you just tell someone, here's the input I used to generate this commitment. Okay, so that's all a commitment scheme is. An alternate view that maybe, again, like for some people, may be easier to process is imagine you had an entity that you trust. Like basically that entity is going to act like an envelope, right? So what you can do is you can commit by sending something to this trusted entity, and the trusted entity will tell other people that a message was committed, right? And they won't say anything else. So anyone can ask them like, oh, was it larger than 10? Was it smaller than 10? And they're just not going to answer that. They'll just say there is a message. And the player can tell the trusted entity, now it's okay for you to reveal. And then after this, the trusted entity will tell others, what the message was. Okay, so really think of it like a commitment scheme is kind of like a digital envelope. They can only be opened when the committer decides that they're ready to reveal it. Okay, now again, so in practice, this alternate view is not exactly what happens, right? So in practice, the commitment is an actual string of bits, right? So the commitment is not actually locked behind a trusted entity that no one can interact with. In reality, it's a string of bits. And so because it's a string of bits, people can try, they can hack around it. They can say, ooh, because the first bit is 1 and the last bit is 0, I think that means it's more likely that the commitment is one thing instead of another. So they can try to do that. And what's widely believed is that if you use a hash function that, if you use a secure hash function, then this scheme, this process doesn't work. Okay, so let me again give you a canonical application. So canonical application 1 is in an auction, I want to submit a sealed bid, but I would like to only reveal that bid after all the other bids have been submitted. So what's the solution I would like to use? I would like to post to the auctioneer and to everyone else a commitment to my bid. And later, only after all the other commitments have been submitted, then it's time for everyone to reveal. And I'm going to reveal my bid in the randomness after everyone is committed. And the idea, as you can kind of see through, right? Like if this was really done through a trusted, a trusted center, that indeed no one would learn anything from the commitments because the trusted center just collects them and doesn't share anything. And then only after the reveals are made does the trusted center start sharing things. Okay, and so again, the representative concern is that someone, when they see my actual commitment, they might learn something about my bid. And what you get from this ideal commitment scheme is a property that's called statistical hiding. And what it means is you actually get something very strong, which is that if you use, this ideal scheme, then for any 2 distinct bids, the distribution over commitments that you get is actually exactly the same, right? So what that means is that someone can look at your commitment and they literally learn nothing, because no matter what you committed to, the distribution over commitments would be exactly the same. Okay, so that's a useful property, and this is a property that some real commitment schemes actually have. And what I want to do now is I want to give you an application of commitment schemes in pure auction design before going on to the last basic primitive. Okay, so at EC 2018, the best paper that year was called Credible Mechanisms by Akbar Pour and Lee. And there's a lot of stuff in that paper, but the result I want to focus on is they showed that the only incentive compatible, credible, revenue maximizing single item auction is the ascending price auction. And one thing that's a little bit undesirable about that is that the ascending price auction has an unbounded number of rounds. So let me quickly just go through these terms for those of you who aren't familiar with this result. I'm not going to spend a ton of time fully explaining the result, but I just want to give you, quickly go over the terms. So incentive compatible, hopefully, if you're in mechanism design, you've seen that before. It just means that it's a dominant strategy for the bidders to bid truthfully. Credibility was a term that they introduced in that paper that's becoming more common in the EC community. But what that term means is it means that over all safe deviations, the auctioneer maximizes their revenue by running the auction honestly. So what is a safe deviation? Well, the auctioneer is allowed to cheat. They don't have to follow the auction rules they promised, but it shouldn't be detectable, right? So like if you tell a bidder like, hey, I know you submitted a bid of 10, but you need to pay me 30, then the bidder would know that you're cheating them. But you should cheat in a way that is at least possibly consistent with some state of the world of what the other bidders did. So for example, the second price auction is not credible. So one safe deviation for the auctioneer is after learning that the bidder one submits a bid of 10, they can say, bidder one, you won, and you have to pay $9.99, and that's because bidder two submitted $9.99. The first price auction is credible, right? So every safe deviation has to pick some bidder J and tell them that they won and pay BJ, and the best thing the seller can do is to pick the highest bidder. So what we can kind of conclude from this awesome paper is that if you take a pure mechanism design approach with no cryptography, then there is, I'm interpreting part of their result as an impossibility. It says if you want incentive compatibility plus credibility and optimality, then you need an unbounded number of rounds. So let me tell you something you can try to do with cryptography. So I'll call this the commit reveal auction. So all bidders, please commit to your bids. The auctioneer will forward all commitments to all bidders. All bidders, I'll then say, please reveal your bids. I'm not going to give you any more bids besides the commitments I forwarded to you. And the auctioneer then forwards all reveals. This is a typo. And then they run the second price auction. So that's something I can do with commitment schemes. And this is actually not credible. Okay, so why is it not credible? Well, here's a safe deviation for the auctioneer. So the auctioneer can commit to bid J for all integers J. So they can make lots of commitments. Forget integers, they can do it for every, not every rational number, but lots of numbers. And they forward these commitments to all the bidders. So they're still submitting a bunch of fake bids. And after all bidders reveal, they say, okay, I see that the highest bid was 15. And I'm just not going to reveal any of the bids that were bigger than 15. I'll reveal all the ones that were smaller. And this is a safe deviation, right? This is consistent with look, bidder one, I don't know what happened, but there's a bunch of bidders who had, I don't know if it was latency issues or they just got bored with the auction, but they dropped out and they didn't reveal their commitment. There's nothing I can do about it. It's cryptographically secure. So that's credible. Or sorry, that's a safe deviation. It's not credible. And so what you can see is that, just using cryptography also does not solve this problem. And maybe I'll rephrase this. Just using basic cryptography does not solve this problem. I am going to show you some very fancy cryptography in a few slides. But let's start with this for now. And here's something you can do that tries to do a little bit of both, right? To say, well, what if somehow I'm going to try and charge fines to the bidders and who don't reveal. And what I need to do is I just need to say okay, if they pay the fine to the auctioneer, that clearly doesn't help. But I want them to pay the deposit that they lose, just provably not to the auctioneer. So you could pay the winning bidder, that's fine. Then the winning bidder knows that they didn't go to the auctioneer. If you want to do this on a blockchain, you can just burn it. That's possible to do too. And now there's a mechanism design question, which is how large do the fines need to be in order for this simple auction to be credible? And the answer is that for MHR distributions, there's a sufficiently large fine that works. I don't want to get into what these terms mean. Basically, for some distributions, there are large enough fines. For other distributions, there aren't large enough fines, right? Then you get here by doing what looks like classical auction theory. Maybe let me skip through this. We had a follow-up paper that showed that there's a slightly more complicated mechanism design, but still using the same basic cryptography that can be credible for all distributions. But what I want to take away from this is that these papers use both cryptography and mechanism design. And this is not the only paper. These are not the only papers with this property, but it's the one I know best to present. And using both, you can get a better solution than just trying to use raw cryptography or raw mechanism design. So what I'm trying to pitch here is that you can use cryptography as a toolkit. And I hope that after this talk, you'll kind of see some examples, but it doesn't replace mechanism design. Okay, I'm again going to quickly check the chat. Oh man. Okay, I'm ballparking. It seems like the questions have been answered, but I'll look again afterwards. Okay. So the last basic cryptography that I want to cover is called digital signatures. So digital signatures, think of them as like it's trying to mimic an actual signature. Okay, imagine that physical signatures were secure. This is what it's trying to mimic. So what does it do? So you have the signer. The signer is going to randomly generate a secret key and a public key. They keep their secret key and they share their public key. They have this function sign that takes a message and outputs a signature using their secret key. There's this public function verify that takes as input M, a claimed signature, and the public key outputs yes if and only if sig was proper, if and only if sig is a proper signature. And then here's this ideal property, right? Which again, in practice, you don't get this strong property, but it'll help you understand kind of like what are you getting, is conditioned on the public key, conditioned on seeing any number of signatures for any set M. If I then ask you, what does a signature on M prime look like if M prime is not in M, you have no idea, right? So even conditioned on knowing PK, even conditioned on seeing lots of signatures, you still don't know what's going on for one you haven't seen yet. And again, there are not constructions that get you exactly this, but I think this is the right way to understand what a digital signature is generally doing. And again, the alternate view is just to think of it like, physical signatures. So you have a trusted entity. Any player can send a message and say, I want to sign this. And then the trusted entity will correctly answer queries of the form, did player J sign message M? Okay. And yeah, again, what you want in practice is you want it to be computationally hard to forge signatures. So let me give you two sample applications. So again, one sample application, or sorry, I think just one sample application is signing transactions, right? So say Alice wants to pay Bob 10 coins in a cryptocurrency, and I'd like to make sure that Alice actually wants to pay Bob 10 coins in a cryptocurrency, and it's not just Bob trying to steal Alice's money. So the solution you should try is Alice should digitally sign the statement, Alice wants to pay Bob 10 coins. And a representative concern is that Bob sees Alice's signed transaction and Bob says, cool, Alice wanted to pay me 10 coins, but I'm going to change it and try and claim that she wants to pay me 100 coins. And I'm going to try and make it seem like Alice signed this statement because all I did was I added a 0. Right? And this ideal scheme that I proposed is non-malleable. Okay, so non-malleable is a term used by cryptographers. The formal definition is much more intense than what's on this slide. But again, with this ideal construction, basically what you get is that even after seeing the signature of Alice wants to pay Bob 10 coins, by this last bullet, Bob learns nothing about what a signature is supposed to look like if I add an extra 0 in there. Right? So this is really key that it says, even if you just change what's being signed slightly, you have no idea how to sign it, even if you've already seen a signature of something similar. Okay. So let me again pause here just to check. Cool, for questions. So that is the end of the basic stuff. I am now going to go through two fancier cryptographic primitives. Okay, so fancier in the sense that they're more recent. VDFs are very recent. In ZKP, the concept is, I think, harder to parse. VDFs, the concept is easy to parse. It's just it's very recent because they're hard to construct. Okay, so let me try and get across zero knowledge proofs. So zero knowledge proof is basically it's a way to prove something, right? So say that you have input X in some domain, and you have a predicate that says that everything in D is either true or false. Okay, so what is this proof function? It's an algorithm that takes as input X in your predicate, and it's supposed to be like a randomized proof that P of X is true. Okay, there's a verify function, and the verify function will take as input X and anything used to prove X, and it should output yes if P of X is true. And if P of X is false, then verify of X and anything should equal no with extremely high probability. So it's okay if there's a tiny probability of fooling the verifier, but it should be ridiculously unlikely no matter what proof you include. I'll give you an example of this to see how this works. And here's what zero knowledge means. So this is a little bit, I think, weird to think of the first time you see it. I will give an example that I think will crystallize it a bit. But what it means is like, look, when you're generating a proof, this is a randomized process, right? So I'll call dist of xp. This is the distribution of proofs that you produce when you run proof of xp. Now here's like, what does it mean to say that you learned nothing? This is what zero knowledge means. It's like, well, if I can sample from this distribution, right, just by knowing x, just by knowing p, and that p of x is true, then like, what have I really learned by seeing proof of xp, right? It's just a draw from a sample. It's just a sample from a distribution that I already knew. So have I really learned anything by seeing that? Okay, I'll give you an example of that in a second that'll make it more concrete, but like that's the formal definition. Okay, now again, what it's trying to simulate is this trusted entity where like any player can send X in a predicate P in a real, like a real proof, like we think of proofs, that P of X is true to the trusted entity. And then, players can send whatever messages they want to each other claiming that something is true. And then the trusted entity will answer queries of the form, is P of X true? Right? So think of this as like, yeah, I mean, that makes sense. If I trust the trusted entity and I know that they're only going to answer the queries correctly, and I asked the trusted entity, is P of X true? And they said yes, then I know it's true. But like, what have I really learned other than that P of X is true? Right? So that I think really captures like, clearly I've learned nothing. And then the question is, how do you, make that a cryptographic definition? That's what the above stuff does. Okay, so the sample used for this is in, there's probably a couple terms for this, but like Zcash is one, I think, or Monero is another. Sorry, Monero doesn't do zero knowledge proofs, but Zcash does, and the term for these is like privacy coins. And the idea is that Alice would like to pay Bob 10 coins, but she doesn't want anyone to know that she's spending money. She doesn't want anyone to know that Bob is receiving money, and she doesn't want to know how much money is being sent, right? So, so what can you do? Well, I mean, here's something you can do. So this is, I put roughly here because I don't think this is exactly what they do, but just with the limited language we have so far, think of it like this. So Alice is going to take sender, receiver, amount, and a signature, and she's going to hash it. And she's just going to post X. That's going to be her message. So everyone's going to look at X and just be like, well, that looks like a random number. But she's also going to include the predicate, right, is X the hash of something of the form A, B, C, D, where A does have at least C coins to send, D is a valid signature of A, B, C, and then Alice is going to write a zero knowledge proof of this, right? So the idea is that all she's going to post is this hash, which looks like, just a random number to everyone, and a proof that actually inside this hash is a valid transaction, right? And so again, the representative concern that you might have here, besides this, right? So there's the zero knowledge, which I think here, if the proof really works out, is not a problem, right? But the other concern you might have is that like, oh, maybe someone's going to post a fake proof, right? So there's an invalid transaction and I don't know it because all I saw was a hash of an invalid transaction. That looks random to me. Well, this proof system, what it promises you is like, well, if that's the case, then the zero knowledge proof that they included is not going to succeed, right? So, okay, and then again, the representative concern too would be that Chuck learned something about X just by seeing the proof, right? And what you should think through is like, well, again, Chuck knows the distribution that the proof is drawn from. He knew what was going to happen, and then he just saw a sample. So like, what did he really learn from this? He could have just drawn that sample himself. Okay. And what I want to do now is I'll give you an example of an actual zero knowledge proof, just to let you see it. So say that the domain is all colorings with 3 colors on some graph, and the predicate is true if it's a valid 3 coloring, right? So a valid 3 coloring means for every edge, the 2 endpoints should have a different color. So here's what the prover does. The prover randomly permutes the colors, right? So it has a 3 coloring in mind. It randomly permutes the colors and commits to them, right? And then what the verifier is going to do is they're going to pick a random edge and ask to see the colors of those endpoints. And then what the prover is going to do is they're going to reveal them, but only those 2 endpoints. And then you repeat this as many times as you want. Okay. So now what do you do? So first is like, look, if what you have is not a valid 3 coloring, right, then like you are going to get caught eventually. Because if what you have in mind is not a valid 3 coloring, there is an edge in your graph where 2 things have the same, 2 endpoints have the same color. There's a 1 in n squared chance that you get caught. Oh, so this is wrong. This should be 1 minus 1 over n squared, so, or 1 minus 1 over m, the number of edges. And you're eventually going to get caught. Okay, so there is not a good way for you to cheat this. On the other hand, what does the zero knowledge mean? The verifier, like, they're just seeing 2 distinct random colors, right? That's all they see in the proof over and over. They see a bunch of these commitments. They never learn what's inside the commitments. And then they just open it. They're like, yep, that was 2 random colors. Yep, that was 2 random colors. Yep, that was 2 random colors. And that just happens k times independently. And so I think it's, so this is kind of like what this definition is getting at, that like you really learn nothing other than that it's a valid 3 coloring by this. Okay, and just let me actually skip this. Okay, so let me again take a very quick peek. Okay, so Clay asked a good question about how Alice's message actually affects the world, because nobody can figure out how much money to send until that's revealed. So in the privacy coins, nobody can actually look at the state. Where is this? Nobody can actually look at the state of the blockchain and know who has how much money. So that's by design. All that happens is but it is still internally consistent. If someone says, I would like to pay you 10 coins on a privacy coin, then you can say, okay, but what you better do, you better write this statement and you better sign it and then hash it. And then you better post it to the blockchain. And I better see that zero knowledge proof checks out when you write this, right? And if the zero knowledge proof checks out, then I sort of think of it like, well, the blockchain knows how much everyone has. Or if you want to think of it in this alternate view, the trusted entity knows how much money everyone has. It's just that the trusted entity is not sharing that information with literally anyone. So you can kind of think of the blockchain behind the zero knowledge proofs as like being this trusted entity, if that makes sense. Let me see. I don't know if that answered the question. But I am going to, cool. All right, I'll answer it more after. Okay, so now what I'm going to do is wrap up with VDFs. And I think I know it's my own fault that I started late, but I might go 5 minutes over since I started 5 minutes late. I don't know if that's kosher, but that's what I will do. Sorry. So for verifiable delay functions, here's what they're trying to do. So this should seem like, how the hell can you get something like this? But here's an ideal verifiable delay function. I just want a function f such that computing f of x takes time at least t, right? I want that to be true, and I want that to be true kind of like no matter your hardware, no matter your algorithm, stuff like that. Okay, that sounds a little bit weird. The other thing I would like is I would like it to be easy for you to prove that you've correctly computed f of x. Okay, and so this one I think is easy to view through this trusted entity, which is like the trusted entity samples a uniformly random function f, and any player can ask this trusted entity at any point in time, what is f of x? And then the entity will just kind of like sit around, and then they'll answer after T rounds. Okay, so that's how you should think of a VDF if done correctly. Okay, now in practice, obviously, this is like, okay, well, what happens if I coded up an algorithm for F and someone else finds more efficient code? Someone else designs better hardware. Someone else like buys more hardware, something like that. So what happens in practice is that people believe that there exist functions that are highly non-parallelizable. Okay, so what this means is they really believe that the best way to compute them is just sequentially to do some operation over and over and over and over and over again, and that that operation cannot be parallelized, that you need to take these steps sequentially. So that's the theory that people really believe that. So now what you still have to interact with practice, because like, yes, you can always have better hardware, but like it could be that you spend a lot of money designing the best hardware for your particular sequential operation, and then you can reasonably believe that you have a pretty good VDF. Okay, but again, the part that's related to theory is, can you design a function that you really believe that A, you have the best algorithm to do it, and B, that algorithm really requires doing things sequentially. That's kind of the key theoretical part. So a sample use for this, right, would be, again, a sealed bid auction. And so what I might do now using just pure cryptography is I would say, well, between 0 and T, I would like all players to submit their bid XORed with F of a random number. So what I'll ask players to do is like, hey, at minus T, pick some R, and then compute F of R by times 0. Between 0 and T, output this. And then sometime after time T, I'm going to do a second price auction. Right. And the idea is that like, and the idea, right, is that like, well, between 0 and T, nobody else can learn your bid if the VDF works. And that after T, everyone can figure it out pretty quickly. Okay. And so this actually would be credible using just pure cryptography. You have to do like, a little bit of mechanism design to confirm that it's credible, as long as the auctioneer uses the optimal reserve, but it's a lot shorter than the previous one. Okay, so again, so this is going to wrap up this portion, and I'm just going to kind of like whiz through the second half in 3-ish minutes. So just remember, I did give you the disclaimer that cryptography is subtle and it is hard. And if you want to use cryptography rigorously in your own protocols, you will need to consult formal definitions. On the very last slide, I got a recommendation for a cryptography textbook from a colleague that I'll put up there. But I do believe that if you felt like these slides were accessible, I think this is sufficient to understand how it's used elsewhere. And I think it's sufficient to understand whether you want to use it. Okay, and then if you really want to use it, then you got to do the work and either talk to a cryptographer or read the book or something like that. But I think this is fine to know whether you want to use it. And there are actually some cases where this lens can be formal, right? So if you find a protocol that uses cryptography, now you understand it because you understand ideal constructions. And you say, well, even if the construction had ideal cryptography, I still have a deviation. Well, then like that just makes your result stronger, right? Because that's completely fine. You say, well, I'm letting the protocol have more power. That there's nothing informal about that, right? So that's great. So that's already, if that's your goal, then you can do that completely formally. The other thing you can do is like, you can say like, well, look, my protocol has all the properties I want, unless somehow someone found a hash collision or a commitment collision, right? And then you just say like, well, but I used a collision resistance hash function. And so if that happened, that would contradict that the hash function was collision resistant. So that's something that I think is within the scope of, the EC community. We can do stuff like that. And the point is like, this is this is a very special case of what cryptographers do more generally, right? So what cryptographers do is they show that I've designed a fancy protocol. And if this protocol doesn't have this property, then some fancy property of the cryptography I use doesn't hold, and that's a contradiction, right? So there are some very special cases of that I don't think are so fancy, that we can't do it. But some of them, the more advanced ones, there's a lot of machinery and cryptography to do that well. Okay. There actually is a whole lot more out there that I didn't get into. I'm not even going to read. And oh man, I will quickly pause and apologize. Apologize for going over. I may just I'll just go for like another 2 minutes, just to give like this really brief taste of what's out there. But then I'll stop for the poster session. Okay. Okay. So I think this slide is, I think, the most important part of the second half of the talk. Is just that cryptography gets you a really far part of the way, right? So just by digital signatures, you cannot forge transactions. Just by hash pointers, you cannot retroactively change the contents of a block. And just by, we were able to do proof of work using hash functions, you can't permanently censor a transaction from entering Bitcoin, for example. So state-of-the-art cryptography is really good, and it does let you do somewhat magical things. On the other hand, it's not like, it's not like a magic sword, and there's still a lot of mechanism design that needs to be done, right? So like in a longest chain protocol, like no amount of cryptography is going to force you to point to the longest chain. And no amount of cryptography is going to force you to broadcast something when you're supposed to broadcast it. And no amount of cryptography is going to force you to include some set of transactions in a block when you could instead just include a subset and pretend that that's all you heard of, right? So these are not cryptographic problems. Cryptography can help you solve them, but like you're going to need to do mechanism design to solve these. And so so the last thing I was going to say was just like, look, there is some existing work. It's actually already kind of huge. I think it's slowly making its way more and more into EC, but I think it should be huger. And so there are some themes. I think maybe what I'll do is just go through maybe these bullets. So I have 3 things. I'll just say context for this agenda. So cryptocurrency protocols propose behavior, and they claim it matches the incentives. And this is getting harder and harder as cryptocurrencies have more and more functionality. The incentives are becoming more and more challenging, and it's absolutely the state. It's not like there's a perfect solution and we don't know how to prove it works. I think for the most part, no one knows what to do, and everything changes. Like every year, everything changes. And I think there's a huge need for modeling and analysis of existing protocols, and also to design novel things. These were some quick examples that I think I'm going to skip. And I will just skip through enough of this to get to my context slide. So here there's a specifically huge demand for auction design in the blockchain space. So for example, this paper I cited of Tim was actually kind of like solicited by the Ethereum Foundation for someone to do a formal analysis of their EIP 1559 auction. So even the cryptocurrency community is realizing that there's a need for real auction design and rigorous analysis. And so kind of like context for what's happened is like, initial blockchains just use the first price auction. The community is now realizing that that's undesirable, and they don't know what to use. So EIP 1559 seems pretty good. But I would say it is still a major open question. What format should be used in the long term? What format should be used in different settings, and stuff like that. And the last thing I'll just say is that there are so many design choices made in cryptocurrencies with very little idea of the economic implications. And some of them in the end work out. And we'd like to know how robust they are should the economic situation change over time. And a lot of them don't. Like a lot of them don't. And there are some pretty big blow-ups where like things that had a very large market cap kind of exploded overnight. And it would be nice if we had a theory to understand why before these big blow-ups happen. So that is it. I'm sorry for, I guess, starting late and then running over, even conditioned on how late I started. And basically what I'll say, just to wrap up, is that I hope that the first part of this talk did make cryptography feel a little bit more accessible. And I'm happy to, if people have questions, I'm happy to try and answer them. And I hope that the second part, even though it was brief, maybe gave you a quick pitch for why I think that this would be a good thing for the EC community to have more of. And here's this. This is one book that was suggested to me by a colleague. I'm sure there are many other good cryptography books out there. But if you just want a starting point, here's one starting point. And I will just remind you that the main goal of this talk was I wanted things to feel accessible and feel like you can figure out whether you want to do more of this. But of course, to actually do more of this, you need to either learn cryptography or have some connection to the blockchain community to make sure that we get the models right. That I think that a lot of the work right now is on getting the models right. And there are some concrete open problems in the papers I cited, but it is definitely a tough field to do research in without some connection to the community. But that is possible. So okay, that was it. Thank you for listening. I will minimize and turn my attention back together, and I'm sorry again for going over.